That module is nothing but the ground wave reflection to ray module. In mobile radio channels, single direct path between base station and the mobile station is seldom only physical means for the propagation. This space module, as a standalone, is inaccurate. So two-ray ground reflection model is useful. Based on the geometric optics, the consider both direct and the ground reflected paths. It is the multi-path propagation. It is known as the multi-path propagation. What happens when the signal receives to your mobile? It is from directly from the base station. That is the one thing. Possibilities are there, which is reflected from the ground. That is another. Which is reflected from the building. That is another. Which is reflected from the trees around you. That is one more. And many more paths are there through which the signals receives at the receiver, that is your mobile phone. Okay, that is nothing but the multi-path propagation. So reasonably accurate for predicting large-scale signal strength over several kilometers that use a tall tower height. Assumption is height is the up to the 50 meters of the base station. That we have to keep in mind. Ground reflection 2 ray module मध्ये एक it is only whatever the mathematical we can say representation for this, and in which the height of the transmitting tower, height of the receiving antenna or the receiver, then direct ray from transmitter to receiver, it is the LOS, line of sight, and another one is the reflected ER. Okay, so this particular part is the reflected, which is reflected from the ground. D is the distance between transmitter and the receiver. HT is the height of the transmitting antenna. HR is the height of the receiver, mobile receiver. So two-ray module gives the information about whatever the total electric field receives at the receiver mobile is equal to E bar LOS, that is electric field from direct ray, and another one is E bar Z, that is ground reflected, and which is known as the reflected ray. So let E naught be the E bar at a reference point D naught. So E bar D dot T, that is it's a distance and time function, and that's why E naught D naught by D cos omega C T minus D by C when D is greater than T naught. D is greater than D naught. ELOS we have to calculate, and then E reflected we have to calculate from this equation, and then E total we have to calculate, and this particular equation gives us a E total. So this is the electric field total given by this. Hello, Harshvardhan. Hello.
Yes, sir.
हा अरे तुझं नाव जे लिहिलेलं आहेस ते नावामध्ये रोल नंबर दिसत नाही मला.
हा हा
रोल नंबर लिही आणि त्याच्यानंतर तू हे कर. याच्यानंतर कधी रोल नंबर लिहिल्याशिवाय. मधुरा इज देअर. ऋतुजा. सगळ्यांनी रोल नंबर लिहा अगोदर. ओके, म्हणजे मग कुठले रोल नंबर्स जॉईन करतायत कुठले नाही करतायत ते आपल्याला लक्षात येईल त्याच्यामुळे. ओके, so this is the cosine law, and with the help of the cosine law they have calculated this, and they have calculated for all the things that is reflected ray and the direct ray also. Ground reflected module साठी we have also this particular part we did in spatial communication, also in antenna wave propagation. So the method of images is used to find the path difference between the line of sight and the ground reflected paths. So method of images is that we have performed, that is delta is the whatever the distance is there that we can calculate with the help of this basic equation like the Pythagoras, and that is they have given here. Okay, and at the end, whatever the path difference is there, path difference means it's related to the direct ray which is coming from the transmitter to receiver directly, and another one is the reflected ray which is coming from the reflections from the ground. Okay, and this is for, we can say, the HT plus HR they are going to, that is the reflected ray, and this particular is the direct ray. Second one is direct ray. Some manipulations, or we can say the rearranging the equations, we have kept this particular D outside, and from this D outside, HT plus HR and HT minus HR we are getting. If we uh, further expand this particular HT plus HR square, HT minus HR square, we'll get this, and the HT plus HT minus HT gets cancelled, HR and minus HR gets cancelled, and 2 HTHR and 2 HTHR. This particular the addition, and that is the 4 HTHR. So divided by 2D. So 2 HTHR divided by D is the path difference we are getting at the receiver mobile antenna. Okay, so here is the path difference they have shown. Now phase difference we have to calculate it. We have to multiply that path difference with the 2 pi by lambda. That is the procedure for calculation of the phase difference. So if we calculate the phase difference and putting that particular in the electric field total, we'll get that particular is theta A divided by 2. Theta A divided by 2 is approximately equal to 2 pi HTHR. Is greater than 0.3 radians. So E total, that is total electric field received at the receiving antenna, is equal to 2 E naught D naught divided by D into 2 pi HTHR divided by lambda D is equal to K divided by D square. Where K is the constant, and it is calculated with the help of whatever the numerator values are there. That is E naught D naught 2 pi HTHR. So what they did, that is this PR assumed power is equal to PT GT GR HT square into HR square divided by D raised to 4. So it is approximation made, and they have kept that HT square HR square divided by D raised to 4. Then this is related to the, we can say, the power received, and power received has also the part of the height of the transmitting antenna, height of the receiving antenna, and the distance between the transmitting antenna and receiving antenna. 4 times distance, that is D raised to 4. So this is the very simple, we can say, the expression ground reflection model. With the help of the ground reflection model, one can calculate the power issue, and with the help of the power issue, one can calculate the whatever the loss is there. So this is the one part of the today's lecture. Diffraction is the bending of the wave fronts around the obstacle. Bending of the wave around the obstacle. Diffraction allows the radio signals to propagate behind the obstruction, and is thus one of the factor why we receive the signals at locations where there is no line of sight from the base station. Although the received field strength decreases rapidly as receiver moves deeper into the abstracted, that is shadowed region, and diffraction field still exists. Often has the sufficient signal strength to produce the useful signals. Diffraction basically, you have to keep in mind that it is the bending of the signals. In shadow region also we are getting the signals, and that is because of the bending of the signals. Knife edge diffraction model, estimating the signal attenuation caused by diffraction radio waves over hills and buildings is essential in predicting the field strength in given service area. As a starting point, limiting case of the propagation over a knife edge gives good insight into the order of magnitude diffraction loss. When shadowing is caused by the signal objects such as the building, the attenuation caused by the diffraction can be estimated by treating the abstraction as a diffracting knife edges. So knife edge diffraction model is there where the edges are there. On that particular edges, there is a diffraction and we are getting the signals in the shadow region. Consider a receiver point is R located. इथं R located झालेला आहे. Shadow region. The field strength at a point R is the vector sum of the fields due to all of the secondary hygiene source in plane above the knife edges. Okay. So receiver is in the shadow region and transmitter is going to transmit the signals, but secondary source means they are going to incident on a particular, we can say, object, and from that the diffraction is taking place. From that diffraction, signals are getting at the receiver side. So they have given the illustration of the noise edge depression, knife edge depression, diffraction geometry. Receiver are located in the shadow region. Knife edge diffraction with HP is equal to HR, that is the one thing, and knife edge diffraction for HP is not equal to HR. Simplified diffraction geometry, delta is equal to. Delta always, delta is the path difference they are going to calculate, and path difference for the different, we can say the points they have given. Here they have shown that particular part, and equations are related to the only Pythagoras. With the help of that, some rearrangement of the equations, we got at the end h square into d1 plus d2 divided by 2 into d1 into d2. The angle alpha is equal to beta plus gamma since d1 and d2 are greater than h. That angle they are going to calculate, that is beta is equal to tan inverse h by d1. आता हे h फार मोठा आहे d पेक्षा, and that's why what they are going to do, they are going to write it as a h by d1 only. Gamma is also h by d2, and h by d2 is means h is very very greater than d2, and that's why they are going to write h by d2 only. So alpha is equal to gamma plus beta, and that can be calculated as, that can be written as. Okay, so h by d1 plus h by d2, that is equal to so that can be we can calculate. So this is the electrical length of the path difference is equal to that multiplied by 2 pi by lambda only. whatever the things we got, that multiplied by 2 by lambda, that is nothing but the path difference, 2 pi by lambda into h square d1 plus d2 divided by into d1 plus d2. So this is the part we are getting. Now letting v is equal to it's the Fresnel Kirchhoff's parameter, that is v is Fresnel Kirchhoff's parameter. We can express phi as phi is equal to pi by 2 v square. Phi is equal to pi by 2 square. And for that, what they did, they have taken this particular part, that is delta square, and they have calculated v, that is the Fresnel Kirchhoff's parameter. We can express phi as a pi by 2 v square. Example is given, geometry. Given the geometry in figure 6, this is the below figure, whatever is there, loss due to the knife edge diffraction and the height of the obstacle required to induce 6 dB of the diffraction loss. Assume that f is equal to 900 megahertz. आता इथं 50 मीटरचा ट्रान्समीटर लावलेला आहे, इकडे 25 मीटरचा रिसिव्हर लावलेला आहे आणि 100 मीटरचा मध्ये ऑब्स्टॅकल आहे, and knife edge is at the edge of this particular whatever the obstacle is there. So we'll get that the lambda is equal to c by f, 1 by 3 for meter. It is 900 megahertz. C by f, 3 into 10 raised to 8 divided by 900 into 10 raised to 6. That is 3 by 9, that is 1 by 3. So angle beta and gamma are subsequently alpha can be determined. Okay, so beta is equal to tan inverse of this one, and gamma is equal to tan inverse of this one, d1, d2. Okay, so 100 minus 50 and 100 minus 25. Okay. D1 is the transmitter to obstacle distance, and D2 is the receiver to obstacle distance. हे करायला पाहिजे, आणि they have not given that particular part in this figure, and that's why we have to keep in mind that this particular is in, I think this part is taken from the book, and in that book they have given this particular part. So alpha is equal to beta plus gamma, 2.434, and if we convert into the radians, that is 0.0424 radians. So Fresnel Kirchhoff's coefficient is found using equation 10. P is equal to 4.24. म्हणजे हे जे इक्वेशन बघितलं होतं आपण, कोणतं हे इक्वेशन v इज इक्वल टू, यांना आपण हे काढू शकतो v, invoking the Lee approximation referring the figure 1, diffraction losses can be determined to be a 25.5 dB. For 6 dB diffraction, v is equal to 0, and diffraction height h can be found using the similar triangle. Beta is equal to minus gamma. So from this, h can be calculated. H divided by 200, 2000 is equal to 25 divided by 12,000. H is equal to 4.16. 12,000 is the total distance they have given. Okay, 2000 is the D2. H by D2 is equal to height of the receiving antenna divided by distance in between transmitting and receiving antenna. Okay, so this is the equation formed, and from that the h is calculated 4.6 meter, 4.16 meter. सो आपल्याला जर V0 म्हणजे नाईफ कोएफिशियंट फ्रेशनल किरचॉफ कोएफिशियंट आहे तो 0 असेल तर इन दॅट पर्टिक्युलर केस we can calculate the height. Hence the obstacle height h absolute is equal to 25 meter plus 4.16 meter. It is 16 meter. Knife edge diffraction module, that is diffraction between the direct and the diffracted path, called the path length. Delta is equal to s square divided by 2 into d1 plus d2 divided by d1 plus d1 into d2. Corresponding phase difference, we have calculated phi, which is multiplied by, and the Fresnel Kirchhoff's diffraction parameter is used to normalize the phase term and given as gamma is equal to that particular V is equal to h into root 2 d1 plus d2 divided by lambda d1 into d2 is equal to alpha 2 d1 d2 divided by lambda into d1 plus d2, which gives the pi divided by 2 v square, where alpha is h into d1 plus d2 divided by d1 plus alpha is the angle, and that they have calculated. याच्यामध्ये बऱ्याच गोष्टी क्लिअर होऊन जातील. नाईफ एज डिफ्रेक्शन मॉड्यूल. नाईफ एज डिफ्रेक्शन मॉड्यूल इज बेसिकली बेस्ड ऑन दी it is based on the only the multipath padding at the receiver side, how the multipath padding is there, and with the help of that the equations are written. There is no much more difference from the we can say the space wave communication, whatever the ground reflection module we have calculated. So it is the extension only, and it is very simple. And alpha, beta, and gamma we have to calculate, and from this we have to put all the values and calculate the losses in case of the knife edge diffraction model. Rational zone represent the successive region where the secondary waves have a path length from the transmitter to the receiver, which are n lambda by 2 greater in path length than of the LOS path. The plane below illustrates successive Fresnel zone. Concentric circles which defines the boundaries of the successive Fresnel zone. In Fresnel zones, we know that because of the signals getting at the receiver side from the different paths, and these are the different paths they have shown here. And only thing you have to keep in mind that the multipath padding is there at the receiver side, and that particular part is how one can model. So this is the one of the modeling of the signal received at the receiver side. Diffraction gain due to the Fresnel nappage as compared to the free space loss E field, and the electric field strength ED, nappage diffracted wave, is given by. And E naught is the space field strength in absence of the both ground and the knife edge. F of V is the complex Fresnel integral, and V is the Fresnel Kirchhoff's diffraction parameter. Diffraction gain always one can calculate with the help of the D in dB is equal to 20 log F of V. F of V, a complex Fresnel integral. And we know that the Fresnel Kirchhoff's diffraction parameter. Fresnel Kirchhoff diffraction parameter. Okay. Approximate numerical solution equation GD is equal to 20 log FV can be found using the set of equations given below, different values of V. If it's -1, it's 0. If it's -1 and 0, then it can be calculated in this particular way. And if it is 0 and 1, one can calculate it in this way. We'll discuss this numerical solution in next lecture. Okay, so only keep in mind that whatever the equations we have seen for the Nye page diffraction model, that particular part is the heart of this this lecture. So Nye page diffraction model is there, and that particular model how it is applicable. So two things we have discussed here today. That is, first one is the with the help of the phase difference, how one can calculate it, the loss, and second one is the night phase diffraction model. Okay, we'll stop here.